So far we have seen two different kind of vortex flows. One is forced vortex, another one is free vortex. And we also saw the reason why vortex form, or in what kind of conditions vortex is formed and how it can be destroyed, right? And now in this lecture we are going to do force vortex. So we are trying to understand the dynamics of force vortex, how the shape of the force vortex is obtained. So if you consider this particular flow, this is basically, you can see this is a parabolic shape that you get, right? That is similar to what you get here. So this is the shape that you achieve when you rotate a glass of water, right? If you have a glass of water, you rotate it with your hand, you will get this parabolic shape, right? So why this happened? Why particularly this shape? Why not other shape? So we are going to derive a solution for that, and to be able to derive the solution, we are going to use Navier-Stokes equation in axisymmetric geometry, as we discussed those equations also in the last lecture, right? And in the last lecture, one thing I would like to correct is that here I had used x, rather it is actually r. So this is something that I changed now. So here we have ur, u theta and uz, right, which are the velocity in r, theta and z axis. Okay, that is something we missed to discuss in the last lecture, but these are three different type of velocities we have in radial direction, then in angular direction and axial direction. All right, so in this particular case, we are at the moment solving for force vortex, and we assume that the force vortex is already developed. And what do I mean by that is, so consider you take a glass of water, and when you start rotating the shape, so originally the water level is flat right at the top, but when you start rotating, slowly the level goes down, and then there will be a point based on the speed of rotation when this shape will be achieved, and this shape will now remain constant, right? So in the beginning, you can call there is a developing phase when you start applying a force. So that time the frictional force, or the force that you are applying, that converts into frictional force, and that actually creates this vortex motion, right? And once the vortex is formed, now you're rotating it with constant speed, and it will just maintain this shape, right? So we are going to derive a solution for this maintained shape, not for the development of this shape. Okay, so basically when you start it, if this is the glass of water, this is filled like this, right? And now when you start rotating, this glass of water will become something like this, right? So everything inside is actually also rotating. So here you are basically rotating the glass of water along this axis, and that is how you get this shape, right? So now what we consider is, once this fully developed, so we will call this as fully developed vortex. And we will not consider the transitioning time when it goes from this flat surface to this vortex shaped surface. Okay, and we will consider this fully developed vortex such that we can make few assumption for a fully developed vortex. Let's say we are at the moment considering the force vortex. We can consider ur to be 0, that is the radial velocity, and also uz to be 0. So that is the radial velocity, this is the axial velocity. So basically once the shape has formed and fluid is continuously rotating in angular direction, then there is no ur actually, because there is no transfer of mass from one radius to another radius, and that's why ur is 0, and also there is no transfer of mass in vertical direction. Okay, and that is why both the velocities in vertical and horizontal directions are 0. Okay, but u theta is not 0. Okay, because that is the angular velocity that you are providing. Okay, and let's assume that you are rotating with omega, that is the rate of rotation. Okay, so if omega is the rate of rotation, then u theta will be equal to omega times r. So this is also, you can call the angular velocity. Okay, u theta is the angular velocity, not omega, so that is the rate of rotation. Let's not get confused. Okay, and the rate of rotation actually is related to vorticity. So this is something that we already know, which we did not discuss today, but this is how the vorticity is related with the rate of rotation. So vorticity is generally 2 times the rate of rotation for any angular motion. Okay, so this is well accepted result. This is not something we are assuming. This is how the vorticity comes into picture, and that is why we can simply consider u theta to be omega r by 2. So this is your angular velocity with in form of the vorticity. All right, where omega is the vorticity, and let me make it little better. Okay, so that is what we have. And now, so we have got u theta, but how about du theta by d theta, or anything inside d theta? So this parameter will be simply 0, because we are assuming that flow is fully developed, and whatever velocity we have in angular direction is a constant velocity. Okay, so this is let's say this is an axisymmetric case with constant angular velocity, right? So we know that it's rotating, but that angular velocity is same at all points, and that actually means that at any angle of theta which goes from 0 to 360 degree or 0 to 2 pi, u theta does not change. Likewise, any other parameter does not change with theta, and that's why anything inside this derivative, whatever you put here, this d of bracket by d theta will always be 0 in this developed case. Okay, and now one more thing that we have to understand is that this is, once it is fully developed, things are not changing in time. Okay, so it is unsteady flow, so d by dt term will also be 0. So none of the velocity is changing with time once the flow is fully developed. Okay, in the early time when you start rotating it, obviously it will change with time. So till here this is a function of time, but once it reaches here it becomes unsteady. So this can be considered an unsteady flow. Oh sorry, it can be considered a steady flow, not unsteady, sorry. Okay, whereas this can be considered as transition when it goes from flat surface to curved surface, but once the curved surface is achieved, flow becomes steady, and anything inside the time derivative will be equal to 0. Okay, so this is because of the steady flow. Okay, and that is why the solution we are going to derive is only applicable for this case and not for case 1. Okay. Okay, so let's start with these equations that we have that we already discussed in the last lecture. So here we have continuity equation and Navier-Stokes equation in radial, angular and axial direction. And now based on what we just derived, we can start deleting terms or omitting terms one by one. So here we know that ur and uz are 0, and d by dt and d by d theta term are 0, right? So you can see that here this ur term is 0, uz term is 0, right? And here d by d theta term is 0. So this equation 1 is of no relevance because all terms become 0. Now let's go to equation number 2, that is Navier-Stokes equation in r direction. Okay, so here we have ur equal to 0, this is 0, this is 0, this is 0, and this is 0, this is 0, this is 0, this is 0, and here we have du theta by d theta, so that also should be equal to 0. And all right, and we haven't talked about the gravity, but that is something we are going to do soon. All right, and let me use a different color here so that we are consistent. Okay, in the gravity is something that we haven't discussed yet, but looking at this flow, we can assume that gravity is there in the vertical direction and not in the horizontal direction. And that is why if we define G as, let's say it has component gr, g theta and gz, in this case we will assume 0, 0 and minus g, where z is going upward, right? So that is our g value, which is minus g for the z direction but 0 for the other two cases. Okay, which we can write that here 0, 0 minus g. All right, so and that is why this also becomes 0. All right, now let's go to equation number 2, where we have d by dt term as 0. This is coming 0 because of this, the green color, and then ur is 0, uz is 0, dp by d theta is 0. Here we will use green color here because this is 0 because of d theta, this is 0 because of d theta, and here your ur is 0 and g theta is also 0. So we can see that in this equation all left hand side terms are 0 and only few terms in the right hand side are surviving. Okay, and now let's go to equation number 3, and here again we see that ur uz are 0, uz is 0, uz is 0, uz is 0, uz is 0 and uz is 0. All right, and du by dt is 0 and only these two terms will be surviving. Okay, where this one will become equal to minus rho g. All right, so now we have seen that most of the terms in these equations are cancelled, and that is why the simplified equation we can write are so if we call this as equation 1, equation 2 and equation 3, because the first equation, the continuity equation, is not relevant anyway. So we'll start with equation 1, and that gives us minus u theta square over r is minus dp by dr, right? So that is the term remaining, and then equation number 2 gives us 0 equals mu 1 over r d by dr r du theta by dr minus u theta over r square plus d square u theta over dz square. All right, and the third equation we have is 0 equals minus dp by dz minus rho g. Okay, so these are the three simplified equations we have from the set of governing equations, and now we are going to make use of all these three equations to derive our solution. So let's start with equation number 2, because this looks more complicated than the other two. So and we need to check whether this equation is actually relevant or not. So we can actually write mu 1 over r d by dr r d by dr, where u theta is something we have already defined, and that is omega r by 2, that you can see. So this is omega r by 2 minus omega r by 2 r square plus d square by d z square omega r by 2, right? And you can see that in this equation there is no z term here, right? And this is derivative of z, and that's why this will become simply equal to 0. And if you simplify this equation further, this will become 1 over r d by dr r omega by 2 minus omega by 2r, and this further becomes 1 over r omega by 2 minus omega by 2r, and you can see both these terms are same, right? So this is same as this, so this cancels out and this becomes equal to 0, right? So equation number 2 basically becomes 0, and that is why that is again irrelevant for us. So only equation 1 and equation 3 are relevant, and let me write them down here. So equation 1 and equation 3. So equation 1 is this, and equation 3 is this. So we can solve them individually. So first equation is basically omega square r square over r minus dp by dr, and there should be a factor of 4, right, which we know from the u theta value. Okay, this is basically positive. So this gives us dp as omega square by 4 r dr. So let's say we integrate it, and this becomes p as omega square by 4 r square by 2, plus let's call that is a c1, that is a constant, right? Whereas for the other side we get dp by dz as minus rho g, so that gives us p as, if you integrate, that will become minus rho g z, plus let's say it is c2, that is another constant. And we can see that the left hand side is, we get one equation with respect to r, one equation with respect to z. So here this is p of r, where c1 can be a function of z here, and here this is p of z, where c2 can be a function of r, right? So we have two constants, c1 and c2, but c1 is a constant in r but not in z, whereas c2 is a constant in z but not in r, and we don't know that, and that is why to find p of r z we can simply add these two equations, and this will become rho g z plus omega square by 8 r square plus some constant. Okay, so that new constant actually comes from c1 plus c2, which is simply a constant, that's not a function of r or z. Okay, so that's an absolute constant. So this is the equation that we get, okay, for the pressure condition in the vortex. But now we have to find the constant c, and for that we can actually define a point. So let's consider this image. Okay, so this is the vertex that we have got, right? This is just a representative image, and let's assume that this is the lowest point in the vertex, that when you look from the top, right? And above it is air and below it is water, and that is why this point must be at the atmospheric pressure, right? And let's define our r and z from this point. So if this is z axis, we define r from here, so we can call this point as rz equal to 0 0. Okay, that point we are defining as our coordinate, or origin of the coordinate from where r and z are measured. All right, and if we do that, we can assume p at 0 0 is equal to p atmosphere, because that is in contact with air, right? So here this is air, and what you have here is water. So there is air above, water below, so this point must be at the atmospheric pressure, and that is why we can get the constant c using this. So at r equal to 0, okay, so we already have this condition, so we can now define p atmosphere to be 0 plus 0 plus c. So basically c is equal to p atmosphere, and that actually means that P of Rz is equal to minus rho Gz plus omega square R square over 8 plus P atmosphere, right? So this gives us pressure distribution inside the vortex, right? And now if you want to define the shape of the vortex, so basically this is, let me rearrange it. So this is P atmosphere minus rho Gz plus omega square R square by 8, right? So now you can see this is the pressure distribution in the vortex, right? And this depends both on Z and R. And why there minus sign in front of rho Gz? Because you are measuring Z upward, whereas pressure increases downward. So as you go down from Z equal to 0, this particular value will become positive. So the total pressure inside the fluid will actually increase. All right. So this is what we have, and now based on this we can actually find the shape of the vortex. So if we again use this particular image, so the shape we have is this. This is the shape of the vortex, right? And at this location we know that P is equal to P atmospheric, because that is in touch with the air, that is the interface of air and water, and that's why the pressure at that point must be equal to P atmospheric. So now if you define P as P atmospheric, if P is P atmospheric, that actually means that the pressure on both sides cancel, and this equation gives us rho G Z is equal to omega square R square over 8. Okay, so that gives us Z is equal to omega square R square over 8 rho G, right? So you can see how the Z is following a parabolic value against R, and that is why this shape that you get here, this is actually a parabolic shape which follows Z as a function of R square. Okay, and that is actually given by this. So now if you define this, if this is your Z equal to 0 and R equal to 0, you can actually find the location of the vertex from this point using this particular equation. Okay, this defines the shape of the vertex. Okay, so this gives the shape of the vertex, right? And also based on this equation which we have derived here, this will give you the constant pressure line. So let's say if you go below a certain Z value, let's say if this is your right? This is your z1. So if you put uh, that particular z value, and if you want to find, let's say there is pressure p1, right? So that basically pressure p1 will follow a particular curve that will look something like this, and that tells you this is, let's say, pressure p1, this is pressure p2. So these are all your constant pressure lines, and you can see they are all in the form of a parabola, okay, which is actually defined by, I mean, this parabola is coming, and then the location actually shifts downward because of different z value. Alright, so this is the shape of the vertex that you get from this equation, and also the pressure distribution within the vertex, and based on this you can also figure out what is the maximum pressure at the bottom, or pressure at the middle, or pressure above. Okay. And from this equation, we can also now check whether the Bernoulli equation is satisfied or not. Okay, so the equation we have is this. Checking the validity of Bernoulli equation. Alright, so this is the equation we have got. And if you want to write this in form of Bernoulli equation, what we can do is we write this as minus omega square r square by 8 plus rho g z is equal to P atmospheric, right? And we know that u theta is equal to omega r over 2. So that will make this equation as u theta square over 2 plus rho g z is equal to P atmospheric. And we know that this kinetic energy term, that is the second term, must be in form of must be positive rather than negative in case of Navier-Stokes equation, in case of Bernoulli equation, and that's why let us try to bring u theta square by 2 the other side. So basically it can be done by defining u theta square plus rho g z is equal to u theta square plus P atmospheric. So we have defined u theta on both sides, so that actually now gives us P plus u theta square by 2 plus rho g z is equal to u theta square plus P atmospheric, and we divide this by rho g plus u theta square by 2g plus z is equal to u theta square by 2g plus P atmospheric. And I think we have missed the density term somewhere here. So I think we have missed the density term, and we need to go back and check. So this density term that you see, not that one, I think this density term is actually missing from our equation, right? This one. So we forgot to multiply rho here, so let's do that. So the rho will come there, rho will come here. All right, so there will be rho here, there will be rho here, there will be rho here. So rho should be multiplied at all places, and this will be a, there will be a rho. So basically this equation now will become simplified. Okay, so this will become z equal to omega square r square over 8g. So this is 8, this is g. Okay, so I think this is the correct equation. This is the shape of the vertex, where rho which we had before in the denominator, that is gone. So this will give you the shape. Okay, so that was a mistake. My apologies for that. And we can multiply rho here. There is rho here. So rho here. There will be rho here, rho. Okay, so this equation is now correct, right? So what do you see in this equation is, this is left hand side is the Bernoulli term, right, that we know, whereas u theta here we know is equal to omega r by 2, okay, where omega is a constant but r is not, and that's why this equation will read as p by rho g plus u theta square by 2g plus z is equal to omega square r square over 8g plus p atmospheric. So what do we see here is this, that this is the Bernoulli term, right? We define is b as Bernoulli term, and we see that b is not constant, rather b is a function of r, right? We have this, you can see this is a function of r. That actually means where this is a constant, whereas there is a radius term in the right hand side, so that's a function of r. That actually makes b as a function of r. So right, Bernoulli term is a function of r, which means it is not constant everywhere in the flow field. All right, and that is why, therefore, Bernoulli equation is not applied in the force vortex flow. Okay, right? And now if you go back and remember the last lecture where we talked about the difference between a force vortex and free vortex, we saw that the force vortex is a rotational flow, right? Whereas we know that Bernoulli equation is fully satisfied only in case of irrotational flow. If the flow is rotational, then it is applicable, it is valid only on a streamline, right? And that is something we are going to check, whether it is actually applicable on the streamlines or not. So here Bernoulli equation is not satisfied or not applied in the force vortex flow because the flow is rotational. All right, and now if you want to see the streamlines in a so let's take this image again. Okay, so we know that you're rotating in this way, and if you look from the top view, it will look something like this, right? This is how the fluid is flowing in perfectly circular shape, right? And that is why this u theta that we have, so let's say this says u theta value, which is function of omega r by 2. So at each r, let's say this is r1, this is r2, this is r3, this is r4. So u theta 1 will be omega r1 by 2, u theta 3 will be omega r3 by 2, so etc. So for each r, u theta is constant, right? So for each r value we know that u theta is constant. That actually means that if you take this equation, it fixed r, which is basically representing a streamline of the flow, this term p over rho g plus u theta square by 2g plus z will be a constant, right? Because this term is now a constant and also this is a constant, right? Why this term is constant? Because we are talking about a fixed r value, right? So streamline is actually flowing, is perfectly circular. That means your r remains constant for that streamline, and if it is constant, that means this particular equation will follow this. So basically right hand side term in this equation will be a constant. That actually means that if we define this again as b, so b is a constant on a streamline. Okay, so Bernoulli equation is satisfied on a streamline even for a forced flow case. When the flow is rotational, it is applied on perfectly follows this equation, right, where p by rho g plus u theta square by 2g plus z is equal to constant on a streamline. Okay, so now we will see a free vortex case in the next lecture.